Hello, everybody. Welcome to the last technical session of ISS 2020. And I could not imagine a better way to close the program than to invite Professor Pourang Irani to present, hold forth. He is a professor in the Department of Computer Science at the University of Manitoba and Canada Research Chair in Ubiquitous Analytics. His research is in the areas of human-computer interaction and InfoVis. More specifically, he focuses on in-situ user interfaces, interactive methods and systems for giving end users efficient access to information anywhere and anytime. His interest in translating research outcomes into consumer-ready technologies have motivated his work with the industry. Indeed, he's collaborated with his industrial partners such as Honda Research, was a visiting scholar at Microsoft Research, and he serves as a scientific advisor to several organizations, including the Human-Machine Interaction Lab at Huawei Canada. And without further ado, thank you so much, Pourang, for joining us, and welcome to ISS.
Thank you very much. Yeah, thank you, Joachim, and thank you to the committee for having me give this presentation, and to our sponsor as well, to have proposed my name for presenting today to you all. So in this talk, I want to present, some of the latest ideas we've been playing around, but something that has sort of culminated over the past few years from work in our lab and in collaboration with researchers in my work with researchers. So as Joachim mentioned, I'm going to talk about end user comfort in the design of in-situ user interfaces. And so I'd like to provide some context about what I mean by, first of all, in-situ user interfaces, which I believe most of us are probably quite familiar with. And then I'll talk about, perhaps principles of end user comfort that we've kind of adopted or we are developing to facilitate and inform the design of these interfaces. So if we look at, the development of computing, we look at, an era where we had personal computing, where, and this is what I'm basically using right now to share my slides with you all and this talk with you all. And over the years, of course, we moved to mobile computing, where now, the resources and information can be accessed pretty much as you're on the go. Ultimately, we started talking about, of course, ubiquitous computing, where information is literally everywhere and pervasive in anything. And none of these paradigms have really replaced any of the other paradigms. They've simply sort of augmented and they've sort of expanded, what we can do with computing in our daily lives. And similarly, in situ computing is perhaps what I see as the next wave in terms of, where end user interfaces could be of quite interest. And so I sort of see this area becoming something that's emerging, particularly as technologies are evolving to enable these. And so what I mean by in situ computing is basically systems that support users in the context of a real world activity. So it could be, you're perhaps replacing oil in your car or doing a repair. And the idea that computing can provide you information about what you're doing. It also knows what you're doing and senses what you're doing and gives you access to that information in a timely manner and one that's, useful to the task. Perhaps one of the most familiar with in situ computing interface I refer to is, the idea of navigating in the world. So that's a real world activity. You're moving around the world and you're being given information about, this process. Ideally, it's guiding you, but it's also augmenting your exploration of a particular environment. We can see a lot of this happening in sort of more specialized contexts. So for instance, in the case of electronic repair, machinery repair, the idea of being able to guide users in real time and provide information in the context in which they're actually working. So in facilitating that real world task is becoming more and more prevalent, becoming more and more possible. And so, you can move out from those niche applications and think about, well, how can this actually support other sort of perhaps more daily things that we do? So for instance, assembling furniture together, we know that it's a fairly tedious task. It's something that we may or may not do collaboratively. But you could imagine interfaces supporting this kind of activity, which currently they perhaps don't. We typically go off a paper map, and the task can be quite frustrating at times. But you could imagine that, as you're moving along this process, that you are actually being given information. So it's a real world activity, and computing is actually serving you. So in this way, in situ computing, and another is when you're, doing physical fitness, is supporting that activity. It's there to enable and support what you're actually doing. It's giving the information at the right place and right time. It's typically on the go. It's not pinned to any one specific location. It's often happening as you're moving through the world. It's fairly interactive. So context-aware systems may often sit in the background and sort of sense what you're doing. In these systems, the idea is that they're often observing, and there's sort of this dialogue happening between the user and the systems as such. And finally, they're actionable. That is, the systems provide you with guidance, and the idea is that you ultimately use that information to move along. So if you're jogging and you want information, or you're getting information about, perhaps your heart rate or how fast you're going, and so on and so forth, you can use that information in the context and sort of alter perhaps your movement and sort of move in a different direction or do something else. So then, now given this premise of what I mean by in-situ user interfaces, and it can be labeled in different ways, talk about comfort. And something that, like I said earlier, is something that I've been talking about and thinking about in the lab, but I believe it can really be something that can underpin designs as we move forward. And so the question may say, well, why do we want to discuss comfort in these contexts? So you can imagine, firefighters who are planning out how they're sort of going to mitigate a fire. They're often fully engaged. So in your real world activity, you're doing your task, and the computing is a companion to that activity. It's something that's assisting you. So normally you're quite engaged in the actual real world activity, and the computing sort of sits there and sort of observes what you're doing, but it's sort of assisting you. So oftentimes you're fully engaged. And for that reason, being able to be in a state where you're at comfort, at ease, can facilitate that real world activity. Oftentimes you're cognitive, but not only cognitive, but also your motor abilities are limited. Your hands are very busy when you're working in the real world. And so, how do we support those forms of activity? As I mentioned earlier, these interactions can be quite lengthy. There's a dialogue happening, and you're going through your activity. It could take perhaps a few minutes, but it could also last hours sometimes, and maybe even days. So the interactions can be quite tedious and ongoing. And oftentimes in these contexts, when information is being used to guide your real world tasks, you are often coming up with decisions. You have to sort of make certain decisions and use them to sort of move through this process. But there's another reason too to talk about comfort, is because we are seeing emerging platforms that can actually support in situ activity. So sort of what we refer to as mixed reality platforms, where you can have displays that are perhaps fairly lightweight, but can actually assist you in your world and in the real world task, are platforms that are sort of that are actually becoming possible now to enable us to interact, to explore these kinds of paradigm. And these platforms make that information always available, which is ideal, something that we want. They provide a potentially large display canvas, which is the entire environment around the user, and makes interaction possible with your hands, because it's just something that your hands are available to do what you're doing in the real world, but the display is contextually there. But also, thirdly, talk about comfort is because most of these applications, as we see today, may have been primarily in the areas of niche applications. So firefighters, physicians, maybe in farming and others. But we may want to start thinking about how do we scale for the masses. And so as we think about that, it's important that we consider elements of comfort. So hopefully I've made the case for what it is and see what in-situ computing is, why we need to consider comfort. I want to next talk about what we define, or what at least I think about in terms of talking about comfort. So the dictionary reference to comfort is basically a state of physical ease and freedom from pain or constraint. But it can also go further in talking about the easing or alleviation of a person's feelings or of grief or distress. So that's often the sort of the that's the dictionary reference to comfort. But we can define it in this area to meaning something more specific. So maybe when we talk about comfort, maybe ideas come up to our mind as about how to go about making sort of such systems which provide us this access to this information more comfortable, and that's possibly one definition. And we've moved a long way in going in making that possible. We also, in terms of comfort, we can think of the NASA TLX, which allows us to think about mental demand. Is the task easy or demanding? Is it simple or complex? Physical demand, how much physical activity was required? There's perhaps temporal demand, how much time pressure did one feel, in terms of effort, how hard did you have to work, and so on and so forth. So the NASA TLX provides some elements of comfort, but doesn't really directly address, the concepts of comfort that one would perhaps want to consider in this environment. So what I'd like to share with you is some of the work we've done over the last few years in different elements, in different dimensions of comfort. Some of you may be disappointed that I may not actually give a final definition of comfort. I think it's an evolving definition. It's one that we are defining as we learn through the process. But I'd like to share you some examples of some of our work, which I believe hint at what could potentially lead to comfort and design of interfaces with comfort in mind. So I'll talk about the elements of social comfort, which I'll talk about first. I'll talk about some elements of visual comfort, that go beyond things like resolutions of these displays and refresh rates and so on and so forth. And then I'll finally talk about physical comfort. And I'll also talk about potentially how to design systems that consider these various dimensions of comfort at the same time. So you're sort of cognizant of these different dimensions. I want to also state that these are not the only dimensions of comfort that one could consider. There are many other dimensions, and I certainly encourage and I believe we need to also consider those in order to be able to make this transition of such technologies and make them available to the masses at large. So I'll first talk about social comfort. Sort of start with this video to give you some context about how these technologies can be awkward in certain situations.
Price comparison.
Okay, with what?
What's that?
What are you pricing with?
I'm not pricing anything at the moment. I'm talking on Google Glass.
Oh, okay, this right.
Yeah.
Right. So it's just a very, very brief snippet, but to sort of, situate the fact that, these technologies, and depending on how you interact with them, can be could potentially be awkward, both for the individual or for people around them. And this is an important element, is also, how do you make it sort of something that's at ease and for not only the end user, but also those in indirect interaction with the individuals. So we look at, to look at social comfort, we look at previous studies in the realm of sort of mobile devices and mobile interactions that have looked at these concepts of social acceptability. And there have been a fair number of these that have sort of alluded to elements of what could be considered socially acceptable and perhaps what may not be. And oftentimes in these studies, you may have someone who's performing an action, and then you have those who are observing. So the performer is the end user, the observers are, of course, those in the environment. And then what's common in these studies is the idea that, you will look at the perspective of the performer. So these are typically the performer-focused studies, and there's a large amount of performer-focused studies, so that you're sort of assessing from the end user's perspective, the person who's performing the interactions and the gestures, perhaps how they feel and what's their level of comfort in a certain social context, whether it be at home, in public, at the office, and so on and so forth. So there's a dearth of these types of studies. There's still a few studies that look at, from the observer side of elements, sort of, how do people on the outside see how a person interacts with the devices and the technologies, and what are their perspectives and what are their perceived notions of these. And there are still even fewer studies looking at, the perspective of both. So we were really interested in looking at both, is there a difference in perspective from a performer versus observer, specifically for a certain set of interactions, and interactions as we would consider them to be common for these in situ end user interfaces, which involve, gestural interfaces, maybe voice interfaces, and so on and so forth. And from that, we wanted to be able to say, well, if there's any difference, then perhaps we need to consider the perspective of, perhaps either one of them, or maybe both in the study of these systems. And so we looked at, in a number of studies, we looked at the idea of, the sense of noticeable inputs, which could be sort of these very broad hand gestures, which you're familiar with. Could be voice that we saw in the video previously, or even things like head movement. But we could also consider sort of more subtle input, sort of, something that you're holding in your hand that's not as noticeable. You're not, perhaps, if you're in a public system, perhaps you're not invading in someone else's space, which you could, if you're doing hand gestures, perhaps on a bus or in a public environment. And basically, we looked at a number of these. So, the idea of hand gestures, voice, head, touchpad, and even the idea of using a very small ring that could be fairly subtle. What we see through our studies is that obviously the first thing we see is, and so the ones that are lower here have a lower social acceptability rating. So the ones that are fairly, the ones that are less subtle, the ones that are more noticeable, obviously appear to be less socially acceptable. And this is uniform across both performers and observers. But for those who are subtle, we see some interesting differences. So, in terms of performance, we tend to see them as being more socially acceptable. So the person actually performing these more subtle input with, say, a touchpad or a ring, I tend to accept these kinds of interactions a little bit more comfortably than perhaps someone who's observing and not familiar with the system. And so it leads to some interesting questions, as to, how could these designs ultimately be perceived to be socially acceptable, because this could potentially impact the uptake of such technologies to those who are observing, someone who's actually performing these. So in terms of perceived social acceptability, we see there's a difference in performers versus observers for certain types of interactions, and particularly for the more subtle type, which generally have a higher ranking in the social acceptability scale. We also turned our attention to, is this something that's possible to do using a crowd, where generally speaking, we tend to do these studies in a lab setting. And so that was our next task, was to where we had video clips, which is the general way of doing these studies, is where users will watch video clips. And so we had this both in the lab and the crowdsource. In the lab, however, people performing tasks as well, wearing the head-worn displays in publics. And then afterwards, they both rated it. Both groups rated the head-worn display input modalities, as well as, in the crowdsource, they did the same. So what we actually see is that these displays, or these types of interactions, are typically ranked equally or favorably across both styles. So in both terms of crowdsourcing or lab style interactions, we notice that generally speaking, we don't see much of a difference. So this is actually quite interesting. It allows us to expand these studies, and the idea behind this is it facilitates the idea of performing these kinds of studies for these kinds of, emerging gestures and emerging types of interactions fairly easily, to be able to assess, how people would like to perceive these. So I next turn our attention to the concept of visual comfort. So the idea of social comfort being important is essential, and we keep that in mind, and we'll talk about that. We'll come back to that a little bit later. I want to also explore or present some of the works that we've done in terms of visual comfort. And so in terms of these interfaces where you're actually working with a real world environment, so you're working in the physical world, you need to interact with that physical world. So you obviously need to be able to be present and see the elements there, but you're also receiving information. And so generally speaking, as you're obtaining these through see-through displays, you have one of see-through display, an optical see-through display here on the left, where you can either put a lot of focus on the content on the display, as you see over here, or you try to do some kind of a blending with what's happening in the background. And oftentimes what you see, for instance, on the right, a lot of this information may tend to fade away as is being superimposed over what you see in the back. And so this is the common problem you have. You have a background and you have a foreground, and you're trying to place this foreground on the background, and you notice that there's a fair amount of it that gets washed off. And there's a number of factors related to that. So, in one very good study, there's a number of factors looking at just the outdoor experience for such user systems, for these technical systems. And you notice that, there's a fair number of elements, particularly looking at sunlight and others, that tend to diminish the level of experience. In terms of contrast, people have also looked at, content-based solutions where you sort of try to understand the scene and try to expose the information in an area where you perhaps have high content. So you could move it from something like being above to being below, and you get a better contrast. But having to go between these two elements, moving the content as you're moving around, tends to be quite uncomfortable. There are also hardware-based solutions where you can modulate between the foreground and the background. So you see in this scene, but these technologies tend to be quite large and probably not something that can be actually used currently, at least not yet. And so there's a fair amount of work in this direction. We've sort of taken a more software-based approach where the problem is as such, if you have some color displayed, an interface displayed on your digital display, such as the following year, if it's on a background and the display is yellow, it appears as yellow. But if the background changes to, as you see over here, red, the color starts shifting towards a blend of the two, so more in the orange hue. And if it's blue, it actually comes down quite lower, and that sort of takes over. The background tends to take over the actual display. So if you have a camera here, imagine on your head-worn display, and you're looking at an interface in a scene, such as, say you're in a forest, that would be nice. And so you have the background. Imagine you can capture a scene of the background information. This is where typically your interface would be. You can sort of get a sense of what that color might be. And the target color is yellow. So the idea is that you want to actually present content in that color, and that's important for the display. You want to preserve it. Then the question is, what should the display actually project so that the target color is preserved? And so we model it as such, where you have a background color with that display color that ultimately gives you a target color. And it's a function of, it's a blending function which takes into account the background, the digital color, which is a component of the background material, as well as the rendering of the digital color. And so for this work, we look at the LAB, the CIE LAB color space, which is 16 million continuous color space. Nice thing about such a color space for use, and it has been used in previous studies, is that it's device independent. It provides a uniform distribution of the elements within the color space. And so what we do is we actually divide this color space into a finite number of bins. And this was built off work by Jeffrey Year and colleagues that sort of looked at color naming models in terms of color selection, where adjacent colors are 1 JND away, giving at most a 2.3 Euclidean distance. So you take this huge color space, break it up into bins, and then what we did was we measured the colors that were coming from say a background material, the background LCD, a projected material on a transparent display. And sort of we looked at it across different types of transparent displays. So the one on the left over here is a projection on a see-through transparent plastic. On the right is a transparent OLED display. And so we measured these properties, and you can actually create a profile, a bin profile for each of these types of displays using the colorimeter that we had used in the past. And so from doing that, you actually can create a one-to-one mapping between the colors in LAB space and sort of the colors that you have in terms of bin profile on the actual display. And so you see that on the right-hand side. So on the left-hand side, you have your binned LAB color space. On the right-hand side, you have the binning and the color profiles according to the actual displays that you have. And so what's interesting is with that is you can take a color from LAB space, and you know how it will render on the digital space. So this happens to be the digital space on the small mobile phone, the transparent mobile phone that I had shown you earlier. So in terms of the space itself, what's also nice about the space that not only the distribution of the colors are uniform, but what happens here is that as colors tend to shift away or they start to blend towards the background, they actually blend in a very uniform manner. And so this is a nice property of this color space that we use in this work to be able to say, well, if your colors are moving towards this background, then you know with some certainty, how to retrieve the right color to be able to produce the target, the intended target. So basically, the idea is that you have a target, you have a background that's green, a target maybe in a hue of yellow. And the idea is to be able to identify the color to show. And what we do is, because for each pixel, what we do is we go through this hash table that's created by our profile that I showed you earlier. And you can actually assess the color that you need to render on the digital screen to be able to show this final target color. So this works quite nicely. So here's an image where you don't have the corrected scene on the left, and the corrected one is on the right, where the fidelities of the color are much sharper without losing the transparency in the display itself. Here are some other examples of here. So again, here on the right-hand side, we have the corrected algorithm, the algorithm running the corrected mechanism on these images that preserves the intensity of the colors and sort of the ones where they're not corrected, which tends to blend quite a bit with the background. In this video here, what you'll notice, I'll play the video in a minute, but what you'll notice is that the colors appear to be sharper when the correction is on. So you notice a label at the bottom which says off or on. And so this is when there is no correction applied, and this is when it is applied. And you notice that perhaps the colors tend to be actual sharper. So for instance, on the top, the green will become sharper, the blue will become sharper when the correction is on, or blend further with the background when it's not, for instance. So this was interesting work. Of course, it was fairly computing intensive. It was done at the pixel level. It required, the shaders in the graphics cards of actually a decent heavy powered computer. And so, for instance, on the systems that we run on a day-to-day basis, it may not be practically possible at the moment, but potentially something that could be considered, obviously, down the road. But there are obviously certain small tricks. So this was a work that I came upon recently. And it's very, very simple sort of visual outcomes you can get, where in this work by Kim and colleagues, they looked at the benefits of sort of dark mode, which is typically what you may have put your tablet in, let's say, for instance, when you're reading at night and so on and so forth, for see-through displays. So in dark mode, you have some types of intensities, and when you have it in light mode, you have it, as you see on the left over here. And they did some fairly interesting studies where they looked at acuity as well as fatigue, and were interested in seeing whether such displays can actually benefit. And they actually see that actually dark mode minimizes visual fatigue. And so this is a very simple way of obtaining benefits and minimizing visual fatigue on scenes. It doesn't require a lot of tricks. It's something that's easily accessible. So, we believe that, of course, improved visibility on such displays is extremely important, but there's still many open challenges, obviously, with resolution and other problems with, the optical displays, such as the field of views and so on and so forth. But even with the system that we have right now, and we are trying to sort of push the boundaries of what is possible in terms of these applications, maybe we want perhaps better resolutions or refresh rates and so on and so forth. But quite a bit is still possible using, software approaches. They can be somewhat computing intensive, and what we believe is that perhaps simple approaches can actually resolve some of these constraints. So as in the example given previously of dark mode for reading text, for instance, on optical see-through displays. So next, I want to talk about physical comfort, and I believe this is also a fairly important aspect of in-situ user interfaces. And one that should not be neglected if we have to design these and sort of make these interfaces accessible. So here are some examples of how we could perhaps or envision such types of interactions taking place. You have the interfaces appearing around the user, and they have to generally sort of raise their arm to a certain level. This is also very common, where oftentimes we think of such interfaces as providing mid-air input. Which is highly popular and also very appealing, because you can transfer everything that we do on touch interfaces into this environment, and it would work nicely. So it's very highly popular. It's also highly popularized through movies and other things, other elements. So there's perhaps some understanding of this. But as we've seen earlier, there's obviously elements of social comfort that one needs to consider when designing this. Regardless, there's a big move towards mid-air input. But we can think that, or we believe that actually these types of interactions are unsustainable for very lengthy periods of time, which may be the case with these types of these types of computing, right? So you are perhaps fixing a big engine, you're already using your motor resources fairly heavily, and the idea now to be able to also use that for interaction might actually might not be so ideal. So in some work, we looked at the idea of consumed endurance, which was a metric to look at, quantifying arm fatigue of mid-air input.
Mid-air interfaces facilitate natural user interactions as users freely move their arms in space to interact with the computing system. However, a frequent complaint among users of such systems is the feeling of heaviness and tiredness of the arm, a condition colloquially termed as the gorilla arm effect. To obtain an objective measure of effort for mid-air interactions, we propose a new metric called consumed endurance. Consumed endurance is the ratio between the time used for the interaction and the available endurance time, a measure derived from the biomechanical structure of the arm.
Right. So So in this work, we looked at the biomechanical structure of the arm, and from that, something that you can actually capture using a motion tracking system, and in this case, we did it with the Kinect system, where you can actually capture the different forces acting at the different joints. And what we were interested is what are the forces acting at the shoulder joint, that is, what is the level of torque or force applied to keep your arm sustained in midair. And to do this, we look at the center of mass of this limb, so between the forearm and the hand and the arm, and we sort of look at the mass as being the 50th percentile for both males and females separately, and we can sort of apply certain formulae to be able to obtain that. So sort of looking at the endurance at the shoulder is given by an equation that's actually well known in the biomechanical literature. And what we do is we simply add up the forces over the period of time. So as your interaction is taking place, we add up these forces to be able to assess how much of it is needed or taking place at a given point in time and for a given interaction. So we look at this in terms of interaction techniques, and we look at, well, how can we actually select and which types of interactions are less fatiguing. We also look at areas that are small, for instance. So this is a fairly small area. The one at the bottom is perhaps a larger interaction space. So for selection, you have techniques like using a button on a mouse, sliding, for instance, as you see over here, or dwelling by leaving your hand positioned for a fair bit of time. And like I said, you have a small plane or a big plane. And so we explored a number of these different conditions. And so what we see here is obviously in the blue, you have a smaller grid, and what you have in the green is a larger grid. So, interacting in a smaller grid shows us obviously, and it's sort of expected, but sort of lower consumed endurance. That is, you can sustain that interaction for a lengthy period of time before your arm actually gets tired. And so, clicking is possible with a button or using a second hand, which may not be practical. If you're keeping the same hand, like swiping or dwelling, typically dwell tends to actually work quite nicely. There are obviously other types of interactions that are possible, like pinching or others. Anything that can actually minimize the amount of hand being kept up in the air would be obviously ideal. So like I said earlier, dwelling happens to work quite nicely. And so we take this idea and we say, well, it's useful to have such a metric, but can it actually help us design an interface, and can it inform the design of an interface? And so we look at it in the context of text entry. And so here with text entry, midair text entry, you have sort of a grid laid out in midair, and the idea is to be able to select elements from this grid. And so what we do is we measure the consumed endurance at each point in this grid if you were to maintain the arm at a certain time period. So imagine if you were to maintain your arm for 10 seconds in any one of these grids, you sort of get a map of this sort. So the blue area is where it's closer to the person's body and near their waist, whereas what you're seeing in the red area is something that's a bit further up, perhaps a little bit at the shoulder level, maybe even a little bit higher than that. And so you can imagine laying out the most frequent characters in a certain manner over here. So SEATO happens to be at the bottom because these happen to be more frequently used. And so what we see from our results is that we actually observe the layout with the consumed endurance with our approach, taking less consumed endurance, so requiring less consumed endurance than the one with the QWERTY layout over here. And so the takeaways from this is, when you're thinking about these interactions and considering comfort, oftentimes you need to think about, how do you allow the user to lower their arm to interact? How do you allow them to be, perhaps closer to the body? And this can actually result in some fairly novel layouts and some fairly interesting outcomes. Consumed endurance is not the only model I want to state. There are, of course, others. This is by Yang and Zhang and colleagues who looked at the 3-compartment model from the literature, which accounts for instance, periods of rest in an interaction, which are also important, and sort of expanded the biomechanical model of the upper limb to explore it. So there are other ways also of assessing this, and I believe it's a fairly interesting and rich area to explore. And so the question then arises about, how do we incorporate comfort into interaction design? So this was, again, work that we did earlier, and what we were considering, and this was far before, some of the work that came out on, for instance, the Microsoft HoloLens and other devices that we see, is the idea of being able to position some of these contents on displays. And we sort of saw this work with, stuff that we've seen in the 80s and 70s done with projection-based systems, right? So the digital desk and sort of smart office and so on and so forth, sort of had were presenting these concepts of these interfaces, and us actually believed in the idea of that for minimizing the degree of fatigue. So the idea is that you can actually pull down these displays to an environment where it's closer to the user, by understanding the scene, obviously, and allowing them to interact more fluidly. So this was something that was done back then. More recently, I was actually quite like this work here by Robert Shaw and colleagues at Microsoft Research there, who looked at sample interactions in the space where you can understand these surfaces, and this is their work, obviously, it's not ours, where you can actually now bring touch interactions to these environments by basically allowing the user to sort of open a window and interact with the content right there. So fairly interesting work, and quite nice in terms of being able to minimize what we believe comfort, minimize fatigue, and improve comfort. Along the same lines, we were very much interested in looking at, of course, the idea of mid-air input is very important and very useful, but can be somewhat imprecise for very sort of smaller tasks. And we were intrigued by the idea of using work, or sort of more fine detail work. So in this work here, this is by Barrett Enns, a student in our lab, PhD student, who now is at Monash University, looked at the idea of interacting with your displays in midair, and then sort of refining that interaction with the micro gestures that can be captured, say, for instance, on your finger through a ring device. And so it kind of lead to interactions of this type over here, where you can sort of do these very large movements in the air, and sort of these smaller movements on the ring, on the touchpad. And it tends to work nicely because you can actually bring your hand closer to your body for doing these sort of lengthier interactions with that touchpad. Different ways to combine these different modalities. So you could consider with the head-worn display, you could sort of grasp an object, you can translate it, and then with the ring, because maybe translation is not as good, rotation might be something that you may want to do with the ring. And so you can interleave these different operations, and I believe it could be quite a rich space to explore at large for these types of interfaces for mid-air and in-situ user interfaces. Also work by other colleagues, so Leo and colleagues looked at this idea of a gunslinger. It's a very neat idea. So this was done at the University of Waterloo, where they looked at the idea of replicating gestures close to the body, and literally with the hand lowered to a very rest position, and being able to create a fairly rich syntax of interaction techniques. And resulting interactions of this type, where you can do sort of these fairly coarse movement using tracking of the hand, and then for doing more refined movement, or movements that require a bit more precision, for instance, rotations that require a fair bit of precision. In this case over here, one could consider using the micro gestures that are sort of lowered at a position that's of more comfort and at ease for the user. This is some fairly interesting exploration at the time. And I believe these types of interactions actually could be quite interesting, quite engaging for users. Another type of interface, this is by Davelstein and colleagues, looking at a belt type of interaction, and looking at, also in this case, looking at the perceived level of social acceptance of these types of devices. So again, some fairly interesting work. I believe it's quite useful for these types of environments. So what we see from this work is that nearby surfaces and body proximate interactions can be actually ideal for input with end user interfaces. And we can talk about macro gestures and micro gestures, where macro gestures have a role for allowing coarse motion, and micro gestures to enable precise motion, but also micro gestures allowing more relaxed interaction, which is ideal for sustained and lengthier in-situ activities. So now that we discussed, some of these elements that we've explored in our lab, I want to present some work that is ongoing and is under progress on looking at incorporating the multiple comfort dimensions. So the idea is, how do we incorporate elements of visual, social, and physical comfort as we move forward in designing these interfaces? And so when we're looking at these types of interactions, obviously, one that we're very familiar with is the interactions on mobile devices. But mobile devices, as we have them today, might not be ideal for in-situ user interfaces. They need to be held. They need to be actually taken out of your pocket or a bag or purse and so on and so forth. You need to hold them and interact with them. But they have some appealing elements in that, they're close to the body. You can interact with them. People are familiar with it. There's a level of social acceptance to a certain degree, and depending on how they're being used. And so the idea of being able to take that familiarity and bring it into in-situ user interfaces is of particular interest to us. So where we discussed earlier that in-situ user interactions can at least in some cases can lead to fatigue, and we need to be considered of social awkwardness and also potentially visual fatigue. Being able to use something like a mobile interaction, which is something that's fairly ubiquitous, also socially acceptable, but also provides a fair degree of visual consistency, can be somewhat appealing moving forward. So the idea is, well, can we build these on-body hand proximity UIs? And we are looking at this work, and as well as others, and I know in this space are looking at the idea of being able to project on the palm, for instance, or perhaps around the palm, to avoid issues of such things as contrast and also issues of physical or social fatigue. So the idea is that you wind up with interfaces like this when possible, or when perhaps interacting with them for a lengthy period of time. Obviously, the drawbacks of such interfaces is that they are reduced to a smaller space. So you may want to only use them when, for instance, the user needs a control panel, and that they're going to interact with that control panel for a bit of time. But then to have the interfaces, around the user in midair. So you could think of a pipeline where you need, sensors to estimate hand positions and then do the projection. And this is a very crude demo, one of the earlier ones there. And like I said, much of this work is still in progress. But the idea is to be able to produce this. Now, obviously, this interface is fairly flat. And generally speaking, this is not how the hand operates. The hand is fairly dynamic. Your fingers are constantly moving. And so, one needs to consider how do you actually display content on a deformable palm, for instance, where the interface is constantly changing as the interface gets updated. So that's an example of where we could consider these various dimensions of comfort in an interface. But going forward, I don't believe we have actually captured a full understanding, a full definition of comfort for in-situ user interfaces, and that's something that I would encourage. I like to encourage the community to think about, and would like to talk about an idea of how do you integrate comfort, which we know is a multidimensional element in usability. And in our case here, talked about social, physical, and visual comfort. But obviously, there are other types. There are cultural, environmental, contextual levels of comfort. And I believe it's important to be able to explore and dig into this a little bit further, to transition what I think about these interfaces as being fairly niche at the moment to being something of more useful to the larger public. And largely, how do we make comfort an integral metric in our consideration, evaluation of emerging technologies? It's not clear yet how do we do it. Obviously, we have a fair amount of subjective metrics out there, but there are also mechanisms and objective metrics, such as the consumed endurance that I showed earlier, that could be embedded in the design of such systems as we move forward. And so, thinking about how do we make these, how do we make comfort, and how do we sort of potentially include this in our technologies as we move forward in in-situ user interface, and particularly as we move forward, could be fairly important. So with that, I'd like to end my talk and thank you all. I'd like to thank the committee for inviting me. It's a great honor to be presenting at the ISS. I wish I would be able to present in person, but maybe that'll happen for we'll perhaps see you all at some other year. I'd like to also thank the sponsor company Huawei and the HMI Lab in Canada for inviting and proposing me to present. I'd like to always thank my students, the university, the Canada Research Chair, and the Answer Program for funding our work and for funding many of the projects that were presented here. Finally, the sponsors would like me to present that they also have several current openings at their lab, and would like me to present this to you for those who might be interested in reaching out to them. So feel free to capture this. And again, thank you very much for your time and for the invitation.
Thank you very much for this engaging talk. There are a couple of questions that I would cue in to. Your video seems to be frozen, but other than that, it seems everything seems to be okay. We had perfect audio. It was a great talk, and we have a couple of questions from the audience. So one interesting question comes from Fanny Chevalier regarding color blending. So this is an interesting approach that you presented in augmented reality / mixed reality displays. It's have you thought of how this would impact the display of content where it is important to preserve the color in the environment? For instance, data visualization. It may not be desirable to have, say, a line in a line chart change color because of the background. What would be a good practice to making content visible without compromising the content's general look? Where the color, given if the color of content matters and is important, have you considered this design space?
Yeah, that's a great question. You know, the idea of how to actually make sure that the background is as relevant in the environment. We haven't really considered this, obviously. In this case here, what we were primarily looking at is the idea of being able to blend in sufficiently so that you can actually see the foreground in a manner that's discernible to the user. To be able to actually allow the ability to switch between understanding the background, I think it would largely depend also on what the user is doing. So if the information needs to be displayed right in front of them for what they might be doing, then such considerations as color blending, as I mentioned earlier, become important. However, if it doesn't need to be, if that display and that information doesn't need to be directly and immediately in front of them, then we can consider perhaps techniques that actually shift that content to other areas in the environment so that the user can actually focus on what's happening in the background and what they're actually doing in the physical world. And so for that purpose, I think it becomes fairly interesting to think about, you know, how do we go about thinking about the space that's available to the user and to be able to use that in a way that's efficient to both be able for them to actually do what they're doing to see the background, but then also to be able to see the foreground nicely. Some work that we are also considering is to look at the space in which the user is at and to consider what regions in that space might actually be more suitable for presenting and preserving color. So one could imagine you could detect, for instance, what are the regions, what are the hotspot regions for high contrast. And given those hotspot regions, within the person's field of view and within their potential head motion, those regions could actually be presented with that information. Now, obviously, that would be a case where, you know, the information doesn't need to be overlaid on the physical background itself. They can be around, they're sort of an information bite for the user. So being able to do that kind of operation could be quite interesting, and it's something that we're certainly exploring, but we haven't looked at it totally yet.
Okay, well, thank you for this most interesting question. So we seem to have a little problem with your video, but your audio is coming out in excellent conditions. So I'll go ahead and ask a follow-up question. So I always thought that the solution for this type of displays in real world, that the solution would be to have more sophisticated goggles with opacity control that we could selectively black out unwanted content. But we are still a ways from there. Can you discuss a little bit on how these two approaches compare? Say having an OLED display that selectively grays out or blacks the background versus this very interesting approach that you show with color blending and manipulating color space.
Yes, that's a good idea. That's a very good question. The idea of actually doing it in the hardware itself, if I understand properly, is something that's obviously very appealing because it would actually simplify a lot of the work. I think the issue with doing it that way is that, however, it's very difficult to predict perhaps what kind of background one may be presented with. So in that case, the idea of being able to do the color blending and being able to do it in real time and on the fly is something that perhaps is appealing in those instances. So I don't know if that answers the question or not, but I think that's my perspective to that would be that being able to handling it on the software side of things versus having to leave it primarily on the display might be something that's perhaps preferred. But yet, I mean, I understand the case that in many instances you want to be able to do it also physically. Like, so for instance, current displays have a very hard time adjusting to lighting outside. And so regardless of what you do on the software side of things, the display itself will not be able to handle the extreme amount of light that's coming from the environment. And so for that purpose, I think one needs to consider what are some other approaches. And in these cases, I think some of the more hardware leaning approaches are perhaps better suited and perhaps even simpler than what was presented here.
I hadn't thought of this. So this is I'm still wrapping my brain around the idea that you could also do modulated displays in terms of color blending. So there are a couple of other questions in the terms of what is comfortable interaction. You approached the case of gorilla harms, but again, another question is, I wonder if typing on a virtual keyboard is the best avenue to input text in virtual, augmented and mixed reality contexts. Have you considered other alternatives that are worth exploring that would not build on the keyboard interaction paradigm, say a combination of gestures and speech recognition, for instance?
Right, that's a great question. I think text entry might be going more and more in some of those directions. Obviously, it's not ideal. Speech, for instance, and speech recognition is not ideal in every context, as you all know. And so we still need some level of input. I'm not sure. I'm not a big fan of being able to type in midair in the same way that we use a keyboard, a physical keyboard, because obviously we don't have all the perceptual cues that come with it. The haptic cues and perceptual cues that come with having a physical keyboard. So I'm not sure if we'll be able to design such keyboards with the level of fidelity that you have with current systems. I think we need to instead rethink the idea of text entry for these paradigms and for these computing platforms to the point where we may want to look at multimodal input, such as with voice and some minimal form of interaction, or consider completely a new interaction mechanism. So in the past they've obviously been devices dedicated at text entry. Some of them can be, so for instance, I'm thinking of the Twiddler. It's actually a very efficient text entry system. However, one that has a very steep learning curve, and I'm not sure how many people actually use such a system. But we may want to consider in lines, in terms of thinking about what kind of peripherals might work comfortably when doing text entry, which is a fairly sustained interaction in these environments. And I'm not so sure midair, perhaps, or midair specifically, would be very suited. I know that there's a lot of work in that direction, but is not necessarily it's not perhaps not necessarily the solution that we're looking for at the moment. Yeah.
That ties on to other question that you might not. So the text input modality for these interactions might be short bursts and not continued streams of interaction, but that would take us a little far along. So there is another question from Jean van der Donkt. You have shown many user interfaces with projection and gestures on many surfaces. How about taking the counterpoint? Invisible and I assume inaudible and impalpable UIs. So the unbearable lightness of interacting, if I may add to Jean's words.
Yes, I think those are very interesting directions. You know, the idea of uh, sort of invisible elements. So I'm not quite certain specifically of, you know, are they talking about brain computing interfaces or unaudible, maybe an interfaces that one does not perhaps hear very specifically. Um, but I think that's a very interesting direction. I think the idea of being able to look at, you know, the use of perhaps um, in interfaces that we're just sort of perhaps just familiar with by nature of doing it frequently, and one that you're not sort of porting from other systems. I think a lot of the issues that we face with these environments is that we tend to port legacy environments into these kinds of environments, and we tend to, you know, try to address the issues that result as an effect of that porting. Uh, but I believe it could be very, it's obviously very productive, and I know of work that's going on with, you know, the idea of invisible types of interfaces where, you know, you're seeing some of this work where one is speaking in a very low manner, or perhaps not even, but yet being able to communicate with the system using that kind of an interaction dialogue. I completely agree that those types of interactions at some point would be far more comfortable than the kinds of interactions that require, you know, a lot of physical motion or others that we are seeing today.
So we are going from the invisible computer to the invisible interaction design. That's another interesting question, a follow on here, and that's one that I can relate, although the question is not mine. And this is the conflict that there is in gesture-based interfaces. Have you looked into the accuracy versus precision of these different interaction modalities, such as macro interactions for applications that demand more accuracy? This is a recurrent question from people who are used to desktop, especially computer-aided design type of environments, where you can enter very specific, accurate inputs with, say, textually with the keyboard or with the mouse, and I miss this with the pen or with the hand interactions. Can you comment on this on your context of comfort?
Yes, yeah, that's a very good point. I mean, ultimately, I believe systems that are more accurate, obviously, will be those that are also more potentially more comfortable. I should be careful in saying that. But you know, when a system or an interface is creating a lot of errors, and you know, you're having to repeat your actions and your input and converse with the interface, you're not in a very ideal situation. We haven't specifically looked at accuracy of these macro gestures, so that these very large motions versus the micro movements. I think a lot of this depends on the sensing capabilities and the fidelity of the sensing capabilities to be able to capture these. So, you know, we could do some fairly large macro movements with, you know, fairly high fidelity motion capture systems. But these motion capture systems may not be practical in a sort of day-to-day environment. Either maybe they're too expensive, it's something that, you know, one does not have access to, and so on and so forth. I think the idea of using a macro and micro, as we had shown earlier, which is the idea of, you know, combining what you can do with, you know, large gestures that can be captured using, you know, current computer vision models, and then complementing that with sort of smaller motions or micro motions gives us a good balance, I believe, at this point in time. It's sort of a good compromise until, you know, we get such systems where macro-based systems can be also as precise, and, you know, we can do micro gestures as precisely or as comfortably as, you know, being able to interact with, say, for instance, a mouse on a computer, select, you know, very pixel-sized values. We also have to consider, you know, what are the types of interactions we want to be able to do in situ. So are we actually creating? Is it, you know, is there a lot of creative endeavor that's going on? I think you gave the example of, you know, being able to do some, you know, say, photoshopping and so on and so forth. Is that something that is the applications that we want to be able to do in situ, or are the applications more about being able to probe at the information, query the space, react to the information, the guidance that's given to us, and it's sort of a different nature in to some extent than the kinds of systems where that require perhaps creative endeavor or others. So I think there's a lot at play over here. We haven't particularly looked at the precisions of these systems, but certainly I think it's something that's very important in terms of looking at the comfort element of interaction.
Okay. One last question that are two blended into one, really. It's whether Fanny asks whether my personal comfort can conflict with that of others. How can you reconcile this? And Jover Mullen wonders if you can reflect a bit on how we can best study and design in situ computing interfaces for real situations with real critical tasks. And this is diverging a little bit from your topic of socially embedded computing, and how you can approach that methodology in your research.
Yeah. So I think there are two questions here. The one about I think Fanny's question about personal comfort and how it conflicts with that of others. I think that's a very smart question. Very nice question in terms of yes, my comfort obviously can be a nuisance perhaps to someone around. I honestly don't have a good answer to that. I actually haven't thought about that as much. I mean, I know of situations where it's the case, obviously, but it's not clear that that we could actually consider, or how we can consider it. I should say, however, I mean, the idea that we were approaching it with the observer versus performer studies that we were doing was sort of hinting a little bit at that direction. Is that if you're on the outside, if you're not actually performing, and these sort of technologies are just emerging and coming up, people are not actually using them, or not as much in mass. How do people perceive it? And I think that's where we were trying to hint at with that, but we didn't quite look at specifically, how can you, if you are being sort of, a nuisance through your comfort, is that obviously it's not desirable, but how do we actually accommodate for that? So I think that's certainly a question to keep in our minds as we go forward in this space. In terms of the second question, in being able to build ideal environments to be able to test some of these paradigms, I think it's quite tricky. I think, a lot of this sort of work and being able to advance it in the UI side of things will depend on what we can do in terms of other technologies and say, machine learning and scene understanding and so on and so forth. If you look at a simple example of an activity, being able to sense in depth all the elements of that activity can be quite complex. So we can sense, a few elements at a time through, say, things like wearable devices or sensors that we embed in the environment and on our body and so on and so forth. But to be able to get an understanding of the full range of it is quite tricky. So, and not only that, it actually depends on a lot of the other technologies that are emerging and that need to sort of come together for us to be able to do this properly. So, I mean, I haven't done Wizard of Oz approach at looking at the UI elements of in situ computing to understand scenes and activities and so on. Are perhaps not as complex or sophisticated as they need to be able to design the right interfaces. So perhaps that's one approach at looking at it, and then perhaps some more simulation-based approaches. So if for instance you have this hypothetical environment that you can create in which you can sort of know how the user may respond to certain elements. Then that would work. So for instance, one aspect or one area that we were interested in is this idea of giving CPR. So imagine you need to do sort of pulmonary resuscitation and one is not really familiar with the steps. And so the question comes about is how do you create an environment to explore how the interface should be designed for one who's not familiar with the steps, yet requires the information as they're going through the mechanisms of doing that. There are many elements in that process. It branches out, it's complex. But you could imagine that, the user may branch out into 3 or 4 different areas as they're performing that task. And as they're doing so, you can, perhaps have the interface react to the system, react to that, even though it's not perfectly doing it in the real case. interface. So perhaps those kinds of systems, simulated Wizard of Oz systems and so on, could be designed to facilitate more more in-situ interaction and interfaces, and the design of these and the understanding of these.
Oh, okay. I guess we are a little bit out of time, but Pourang, I did not want to cut you because you were saying so much interesting stuff, and I think this was the befitting keynote to close ISS 2020. So let us give Pourang Irani a round of applause here.
Thank you. Thanks. And thanks for having me.